Yeah, some of you might, if you finished 9, you might want to skip on to 10. But for those of us who are still on question 9, so in this question, I'm going to straight away put that angle there as 30. I like to work out all the angles, and that 60 isn't helpful, whereas that 30 is helpful. So I've got a particle, and everything is smooth at the moment. The smoothness is about to end. All right. But for now, everything is smooth. So the only forces involved are this tension at an angle of 10 degrees, so I'm exaggerating that a little bit, and that is 70 newtons. I've got the weight of the particle, so the use of the word particle says it's 0 dimensions, but it has got a mass, so it will have a weight, and that angle there, I'm going to use a different colour. If that angle's 30, then that angle there must be 60, because if I draw that, that's a right angle triangle. So that's 60. And there's a normal reaction force, which is the slope pushing up on the particle, and that's always perpendicular to the surface. So that's there, and hopefully you can see why that means that's 30. And physicists, forgive me, I'm a big fan of using cos wherever I can. So if you're used to using sine, then go for it. So I'm now going to, because we're on a slope, and forgive me, I forget how far we got, but I'm going to resolve parallel to the slope. So parallel to the slope, and we're in equilibrium here. So that either means I can use force equals ma and say forces up, take away forces down equals 0, or I can just say forces up equal forces down. Same thing, I'm going to do forces up equal forces down. So the forces pulling me up the slope are this 70 Newton force, but it's at an angle. It's at an angle of 10 degrees to the slope, so that has the effect of that. So that's the component of that force parallel with the slope. Pulling down, I've got the mass of the particle, and that's at an angle of 60 degrees to the slope. So that's mg cos 60. The reaction force is at right angles, so has no effect in that direction. And then the second thing we do on the slope is we resolve perpendicular to the slope, so in that direction. So I've got forces up will equal force down. So the force up, which is parallel, there's no angle involved there, is r. Because I'm thinking about this angle here, I don't need to worry about an angle there. But this force is at 30 degrees away from that direction. So that's so because g is a value I know, and we use 9.8 for g, I can use this equation to work out m, and then the one at the bottom I can use to work out r, and that's what I want, the mass and the normal reaction. If you've got your book, the page number is slightly different, so if you are on to question 10, find the page. Just so you can check the answer. So this one actually. page 117, question 12. And so if you're ahead of me, you can check your answers in the back of your book. We're in exercise 5.3. This one here is page 116, question 10. Well, I'm going to do from that. Because we're using M in our second answer, have I made a mistake?
No, I'm just...
I know. I'm always worried. Because I'm using that value here, make sure you store it. So I'm going to state it here and round it to the front of the mechanics exam paper says either 2 or 3 significant figures. We use G to 2 significant figures, but we can give our answers to either 2 or 3. And both books seem to switch between those 2 options, frustratingly, rather than sticking with one. 9.8, no, is G. I've got it wrong. Where have I got it wrong? I've got my M right, but my R wrong. What have I got wrong with my R? M, G.
I got so much wrong.
Go back to them.
Is it cos H here?
I've got 107.
Oh, no, I know what I forgot. Right, sorry. So this was all okay, but when I was... Right, yeah, look, I didn't include... This effect here is pulling it up a bit as well. So when I came to resolve parallel to the slope, it's not just R pulling up, is it? It's R plus 70 cos 80. Okay? So R is equal to... So I apologise, Beth and Lily. And just corrected that. So R is that, take away that. Yeah, so when we resolve parallel to the slope, forces up, I've got the R pulling up, but I've also got the effect of that pulling up. So that force has an effect in that direction, which we used here, but it also has an effect in that direction. Do you want to have a go at the second one? And if you are, again, ahead of me, because this might well be, question 14 is a bit more of a... If you're on 14, the F force is going to be pushing it sort of up the slope. So that's a... I'm not going to go through 14 today, though. I'm going to go through this one, which is question 12 on page 117. You should, the answer to that one, you should get 107 newtons.
Okay. So will you just move down to student services and just sit there, please?
Now my desire to use cos all the time is thrown a little bit by questions like question 10. There we go. So the reaction force is parallel to the slope, but the weight is always vertically down.
Stop and go downstairs. No, I have to do that. We talk about the angles here. So this angle is 90 minus theta. So this angle, because that's a right angle, is theta. And you'll get used to that this angle and this angle are the same. So when I resolve with the slope, going up the slope, I've got 18 cos 30. And coming down the slope, I've got 2g times the cos of 90 minus alpha, which some of you will remember is the same as the sine of alpha. So if I know the angle, I use cos. If I don't know the angle but know the complement to 90, I use sine. So that's how I deal with that. So this angle here is 90 minus theta, so I do the cos of that, which is the same as the sine of theta. And that allows me to work out theta. And the great news, of course, is that theta is clearly an acute angle, so there's only one solution. I'm going to work out lots of different solutions. And I'm not going to make the same mistake again. So going up, I've got r plus 18 cos 60. So those are the two forces pulling upwards, and that's the same as 2g at an angle of theta. And we've just worked out theta. Visual aid. Get 52.7 rounded, but store it, use the exact value. You find you end up typing quite long sort of sums in, but it's always good, I think, to leave it as long as possible before typing in the sum. So you should get 2.88 for that. 2.88 newtons. Can I propose that if you haven't started it, that you have a go at that question 14 before tomorrow's lesson, just as independent study, and that will be a good sort of a test of whether or not you need to do more practice. If you do that question, it's slightly more complicated because you've got a force sort of, rather than pulling it up, it's pushing it down, but I'm sure you've been to work out the effect. You don't get a worked solution with this book, but the solutions are not just answers, so there is help in the back of the book. Right, so we need to talk about friction. Okay, we need to talk about friction. So this is my vision. I normally would do this on the floor, but you can't see it on the camera. So right, just about see that. Okay. Friction's really clever. And I don't know if you've ever stopped to think about this. We know that if something isn't moving, then the forces acting on it are balanced. Okay? So I'm going to apply a force to this box. Okay? Here we go. I'm applying a force to this box. Is the box moving? It is still in equilibrium. So the fact I'm applying a force to the box means that there must be a force balancing that to maintain that equilibrium. And that force is called friction. So at that point, I'm applying a force, I'll call that T, and friction is resisting that force, so we'll call that F, and hence it remains in equilibrium. Right, okay, I'm now going to increase the effort with which I'm putting into it, the force I'm pushing. Okay, here we go. I'm pushing harder. Genuinely, I'm pushing harder. Is it moving? So what does this tell us about friction? It is variable. Friction is variable, yeah. Friction knows how much effort it needs to put in to stop that box moving. And it's not only that, but if I come and push from this side, it's still not moving, and now it's pushing back the other way. How does it know which way to push? So friction is a variable force which opposes motion, or if it's not moving, it opposes the motion that it wants to do. So if I push it that way, it wants to move that way, but friction opposes that. Whereas if I come around here and push it this way, it wants to move that way, and friction is... So it's always opposing either the motion or the direction that it wants to move in. Now, okay, I'm going to push it a bit harder. So Pat has correctly said that friction is variable, but what does the fact that I just managed to move the box imply? It's got a limit. It's got a limit. Yeah, it can only go so far. It's not a force that will keep on getting bigger. It has a limit. So there is a point, as I increase T, where we're still in equilibrium, but it's about to go. So F has reached its maximum value, and we call that point limiting equilibrium. And you may remember when we did moments, we talked about that point when a seesaw is about to tilt, and so the reaction force at the other support was 0. Well, we often do calculations with friction at that point, at the point it's about to slide, because at that point friction has reached its maximum value. So at limiting equilibrium, friction has reached its limiting value, and has reached its maximum value. It's often referred to as its limiting value. Its limiting value, and
What is the size of that value? How can I work out at what point it's going to give up? Well, the maximum value that it can resist me by is actually a function of two things. It's a function of the weight of the box. Heavier things, harder to move. Filing cabinet, harder to move, more force. So it's a function of the reaction force, which of course is, in this case, is exactly the same as the weight in reverse. But it's also to do with the nature of the surface, isn't it? Friction will be, you know, this is quite a slidey surface, whereas if I move it onto the carpet, it's a bit rougher. And we use a constant, which we call, well, we don't call it, we name it after another Greek letter, mu, the lowercase mu, which looks like this. So the maximum value friction can reach, which happens at that point where it's about to move, is equal to this value, which we call the coefficient of friction, multiplied by the reaction force, which of course is affected by the mass, the weight, sorry, which is affected by the mass. At this point, T and F are still the same. Okay? At this point, when T is less, T and F are the same, but F is less than mu r. It's less than mu r. It hasn't reached that maximum value. And then if I increase the force, we then get the third scenario. So I'm going to do that here. So the third scenario so now if T is bigger than mu r, the maximum value of friction, it starts to move. And we know we're then into the world of Newton's second law. We're then going to get an acceleration because the forces are no longer balanced. For the majority of, well, I think for all of today's lesson and for most of tomorrow, we're going to be working with limiting equilibrium. We're going to be working in the situation where we've got forces are still balanced, but friction is at its maximum value. Once we exceed that, we're going to get an acceleration because we're pushing harder than friction can resist. So friction is a variable force that opposes motion but has a limit. And that limit So my three scenarios were, sorry, it's a fairly poor diagram, isn't it? But here I've got a tension a force being applied which is less than the limiting value of friction. So the friction force is equal to it, and therefore it's less than its limiting value. You get to the point though where the force is the same as that limiting value, so it hasn't started moving yet, but it's about to move. And that's where we're going to sit for most of today.
Then if you keep on pushing harder, your force exceeds limiting friction, so you're going to start moving, and that will give us Newton's second law, F equals ma, which we won't have to deal with today. So I'm going to display questions from the text, but the reason I'm using this textbook, because I've been able to buy a copy for all of you, you've got the option of working from it at home, but I like the order it does things as well. That's the other reason. Oh, come on, what's going on here? Sorry. So this example is at the bottom of page 119 if you wanted to look at it, or you can just look at the screen. Now, if you look in your book, you've got, I know I gave you a way to log in with one, but you can actually set up your own CGP account, type in that code. I know for those of you who are sort of like snipping, that's an option you've got there. For those of you who are for who I'm not going to work fast enough, because I'm not, actually I think physics you haven't really done this sort of friction, but by all means jump to page 122 if you feel I'm moving too slowly for you. Okay, so here we've got a force acting on a block, not on a slope, and it's on the point of moving. Okay, it's on the point of moving. So we are at that point of limiting friction where F has reached its maximum value of mu r, and we're asked to find the coefficient of friction in this case. So let's start by doing our normal resolving, and because we're not on a slope, we're going to go horizontally and vertically, and hopefully it's nice and straightforward here, no angles to worry about. It won't last long, unfortunately, but there we go. So go and write your formulas for resolving horizontally and vertically. So I've got a very simple equation for F. So the friction force is 30 newtons because it's on the point of moving. So that's its maximum value. So F is equal to mu r at that point. And I've got what r is. So I know F and I know r, so I can rearrange that equation to work out mu. It's just going to be 30 divided by 4g. Simple as that. Simple as that. So I've got that F equals mu r relationship, which often will link the two equations, the vertical and the horizontal, or if we're on a slope, the parallel and the perpendicular. We should get 0.77.
You don't need to worry about simplifying.
No. You would work out the answer. So the answer and round it. So you should get 0.77 to. That's two significant figures. I don't know what it is to three significant figures because they haven't done that. So let's do a one with an angle. So this is at the top of the next page, 120. And they haven't drawn as many forces there. I know you've got it underneath if you're looking in the book, but try to do it without looking in the book. So in this case, without all the forces drawn, you've got to think which way is it about to slide, because friction is going to oppose that. So you've got to get friction in the right direction. So which way is it about to slide? and then get your friction going in the opposite direction to that. And don't forget you've got the vertical forces as well. You've got the weight pushing down and the reaction force responding to that. Don't worry about where that is attached, so it doesn't make a difference if it's attached there or attached there. It's still at an angle of 10 degrees to the direction, in this case the horizontal. Make sure you've got F going that way because it's resisting the motion. Remember my mistake at the beginning, Q is going to have an effect vertically as well as horizontally. So there'll be a component of Q vertically as well as horizontally. So this looks like a tricky one because I've got two equations but three unknowns, but don't forget the third equation in this story is that, and we're told mu in this case is 0.7. Mu is always a value between 0 and 1, so 1 is really rough and very low is nice and slippy. So what I can do now is I can replace that F with 0.7r and then get the equations the same, or I could do the other way around, write r equals F over 0.7 and replace that r there with an F. I'm going to write both equations as r equals and then make one equal to the other, but there's half a dozen ways of solving these simultaneous equations. So I'm going to replace that with that, rewrite both equations as r equals, and then just make one equation equal to the other. So this is one of those rearrangements where you need everything with a Q on one side, and then you factorise that side. I'm going to multiply by 0.7 to start with. So as I said, you've got another one of these really long sums to type in, and it's all good. And if you're doing physics and you've used sine 10 so cos 80, absolutely fine. I apologise if I'm confusing you. I've got the wrong answer. Oh. Oh no, 7G.
Wait, so
Yes.
what answer is it?
So it should be. Oh, sorry, no, I've got it right.
Yeah.
Sorry, I was looking at 61.063. It should be 62. Right, thank you. That's good. There we go. And is that all we need? I mean, we could then go on and work out f, because that's just 0.7 times that. We're not asked to in this case. So we've got our resolving equations, but we've also got this limiting friction equation. Because it's at the point of slipping, we know friction has reached its maximum value, so we can use that relationship between F and R. So the final example is to introduce a slope. So that's the example 4 at the bottom of the page. So again, see how, if you've got a book in front of you, see how much of it you can do without looking at the picture, maybe covering up, I don't know. Again, it's another frustrating one where we don't know theta, so we're going to have to use some sine as well as some cos. Please let me ask for help if you're not clear on this one. I think that was the most complicated simultaneous equation bit that we had to do. Are you alright, Grace? Are you? So we're still on page 120, bottom of page 120, if you're at home. So no force other than the weight here. So it's about to slide down. So friction is working up. you don't need to write both lines. You can go straight to using sine. So you're going to end up with an equation with a tan in it because you've got a sine and a cos. So you're going to end up with a tan theta equals something long and fiddly with lots of g's in it. But then shift tan of that will give you your answer. Because that's one thing, 3.2 g sine theta, when I divide it by 0.75, I can end up with a very nice number. So I just did 3.2 divided by 0.75. And that's a horrible sum, but I'm in mechanics now, so I'm not expected to simplify that. I'm just going to whack it into my calculator, shift tan it. Bob is your uncle. Hopefully you can see. It all works out okay.
So hopefully you get 0.75 for tan, and therefore the angle when you do shift turn on that is 36.9. So that is friction in 3 different scenarios of increasing difficulty. So on page 22, I recommend we have a look at these questions here. Question 13, and we obviously won't get all these done now. Oh, we won't get any of them done now. Right, okay. Have a go for me at question. So I've already asked you to go at that one. So have a go at question 10 as well.